Okay, next up we have Ruggiero, a PhD candidate at SUNY ESF.
Okay, good morning. So today I will be presenting my work on drivers of nutrient export from New York watersheds. So a common assumption is that land use and watershed characteristics control nutrient loading. And here we ask whether this relationship can be detected across many watersheds. Our objectives were twofold. First, we asked whether watersheds with more human land use export nutrients differently during runoff events. Second, we test whether describing watersheds in more detail improves our ability to predict nutrient export. And so here, detail refers to the spatial scale of land use, which I'll get into. So for the data, New York State watersheds with long-term nutrient and flow data were analyzed. Our focus was on three water quality constituents: total phosphorus, which is TP, and we had 55 sites. TN, total nitrogen, had 23 sites, and SRP, soluble reactive phosphorus, which had 50 sites. And this map is of New York State, and these were the sites that were used in the analysis. And the color, so the watersheds are the little polygons, and the color represents the data availability by constituent. And so these three constituents are important macronutrients that are linked to the harmful algal blooms, with SRP representing the fraction of TP that is immediately available for uptake by the algae. Land cover, soils, and slope information were used to generate watershed characteristics, including this term that I'm going to introduce now, which is presumed nutrient generating areas. So the nutrient data were aggregated into a single metric for each watershed. And so there were three metrics for each watershed: the nutrient export rate during storm events, the median concentration, and the annual average loading rate. So yeah, and then we fit multiple linear regression models to determine how well the watershed characteristics predicted these nutrient export metrics. And so like I've been talking about, land use was described at multiple spatial scales across the entire watershed, within the riparian zone, and in areas defined by the intersection of poorly drained soils and steep slopes. So this diagram with the yellow rectangle can be used to demonstrate the land use at the three spatial scales. So let the yellow polygon represent the entire watershed. The red polygon represents the riparian zone, and the gray arrows would be areas of poorly drained soils and steep slope in the watershed. So any human land use, so like agriculture or urban, that fell within these zones was divided by the total watershed area to calculate human land use at each spatial scale. And then on the right of the slide, there's four data layers. So there's elevation, soils, and land use, and hydrography. And these were the four data layers that allowed me to determine land use at these spatial scales. So nutrient export rate was quantified using the slope of the concentration discharge relationship in log space. So I have some plots showing, so on the left, the three plots show each pane shows concentration on the Y and discharge on the X. And so the first pane represents a positive slope, and this indicates that nutrients mobilize with increase in discharge. And this suggests that the nutrients are progressively dislodged from a nearly unlimited source during runoff events. And we call that mobilizing. On the right pane is a negative slope, and that indicates that nutrients come from a finite source, and thus they dilute as flow increases. And then the bottom pane is slopes that are not significantly different from zero, and this indicates that nutrients release at similar rates across the range of flows, which we call stationary. So to address this question of do watersheds with more human land use export nutrients differently during runoff events, we examine these CQ slopes as a function of human land use in the watershed. So for TP and TN, both developed and undeveloped watersheds exhibited a wide range of slopes from dilution to mobilization. So in contrast, for SRP, more developed watersheds generally showed mobilizing behavior, suggesting human land use promotes the release of immediately bioavailable phosphorus during runoff events. All right, so to test whether describing watersheds in more detail improves predictions of nutrient export, we built the multiple linear regression models using watershed characteristics like number of concentrated animal feeding operations alongside land use at the three spatial scales. So for simplicity, I'm just going to focus on the median concentration of SRP as the patterns were similar for the other constituents. So models using watershed scale land use explained as much or more variability than those using riparian or this PCSA scale. So this suggests that nutrient generating areas across the watershed are important, are as important as those adjacent to the stream. But one caveat could be that our stream network may not have captured all of the hydrologic variability. But this does suggest that it does capture most of it, as you know, these scatter plots look pretty similar. And then the poor performance at the PCSA scale does not mean that the intersection of land use with poorly drained soils and steep slopes is not important. It just suggests that restricting scale lacks, so restricting the spatial scale of the land use means that we lack sufficient information to predict nutrient export at the aggregated level used here. So the aggregated level meaning we removed the temporal component, so we only had one metric, which was the median concentration for the watershed. So human land use did not correlate with nutrient mobilization as expected for TN and TP, although a trend was observed for SRP. Similarly, increased spatial complexity did not improve predictions of nutrient export metrics for any of the three constituents. Overall, these findings suggest that efforts may be better spent on improving the specificity of water quality monitoring rather than adding complexity to predictive models. In Skinny Atlas, this could involve more frequent edge of field monitoring to identify and validate the most important nutrient generating areas, along with the effectiveness of nutrient management practices. So future work will incorporate the temporal component of this statewide data set, enabling more thorough testing of the drivers of nutrient export. Flexible machine learning models, such as decision trees and artificial neural networks, will be evaluated to capture complex interactions among water quality, land use, and other covariates. So I appreciate your attention. This was funded by the DEC, and yeah, I'll take any questions.
Hi, Ryan. Chris Legg, Town of Schenectady Supervisor. Thank you for the presentation. In talking about SRP, you cited CAFOs as one of the contributors. Correct me if I'm wrong, but septic systems are a significant potential source as well. And in your conclusion, you were talking about looking at sampling to include, I assume EDGE is talking about, for example, sampling specific tributaries to see what is coming into the lake through the surface, right, and how that could relate to the use, right, of the land.
Right. All right, so I'm detecting like two questions. One, like, is SRP potentially higher in the subsurface flow? It depends on the soil type. I mean, this is just from my experience, I could say that if the soil type has like a lot of large preferential flow pathways, then the SRP probably won't bind to the soil, so it will be a potential high transport mechanism. But normally phosphorus has an affinity for soil, so I mean, I don't want to say the literature is changing, but I think the literature has trended towards if the water is going to move through the matrix of the soil, then you're not going to have a lot of soluble phosphorus. So that's why the CAFOs and the human land use, we saw a different signal for that for SRP mobilization, because those nutrients are applied directly in the pathway of surface runoff.
Okay, thanks, Ron.
Yes.